Welcome to the third video, trigonometric identities and how to apply them in the unit circle in order to find other trig ratios. Well, first of all, let's deal with this word identity. Here's our first identity. Sine squared theta plus cosine squared theta equals 1. Now, that means this quantity squared plus this quantity squared equals 1. If we look at the unit circle, this shouldn't be a surprise because we have a triangle with hypotenuse 1. Its height is sine theta, its length is cosine theta, and by Pythagoras' theorem we can see that sine squared theta plus cosine squared theta must be equal to 1. But it's always equal to 1. Wherever the position of B, it's always equal to 1. And because it's always equal, that's what we call an identity. It's identically equal. Identically equal. And in some books you see 3 lines there to show it's not an equation, it's something that's always true. Let's see some other identities. We have the double angle identities. There's a really nice proof in your textbook. This is the double angle identity for sine 2 theta. And here's the identity that we've just looked at. Some people call that a Pythagorean identity. And here's a double angle identity for cosine 2 theta. Now they're all proved in the textbook. But let's look at cosine 2 theta because there are 3 ways this is expressed and they're all equivalent. If we just look at the first one, cosine 2 theta equals cosine squared theta minus sine squared theta. But we know from the Pythagorean identity that cosine squared theta must equal 1 minus sine squared theta. And if we replace that here, we get cosine 2 theta equals 1 minus sine squared theta minus sine squared theta. In other words, 1 minus 2 sine squared theta. And the other identity for cosine 2 theta can be proved in a similar way. All of these are in the information booklet. And because they're identities, we can replace cosine 2 theta with any of these 3 things. And we can replace sine 2 theta with this. Let's see some examples. Well, in this one, we are told that sine x is 3 over 4 and the x is in the first quadrant. Now, before we graph it, did you know that sine 45 is approximately 0.7 and sine 60 is approximately 0.9? And here we have sine x is 0.75. So if you think about it, the angle we're looking for must be round about here, roughly. So this is what we call angle x in this problem. And we have to find cosine x, but without using a calculator and without knowing the angle x. And that's easier than it sounds, because from the first identity we know that cosine squared x plus sine squared x is 1. Another way to write that is that cosine x is the square root of 1 minus sine squared x. So in this problem we have cosine x is the square root of 1 minus 3 over 4 squared, and if you develop the square root there you will find that gives root 7 over 4. Now we should be a little bit careful. We've done the square root, which is as a number, plus or minus. But look at how the unit circle helps us. We know we're in this quadrant. In this quadrant, all the ratios are positive. Therefore, we want the positive root, not the negative one. Let's do sine 2x. Well, we know the identity. It's 2 sine x cosine x. And we're given sine x. So we get 2 times 3 over 4 times root 7 over 4. And that simplifies to 3 root 7 over 8. Okay, let's take it on to the next page because we've run out of room there. Now, cosine 2x. Well, the quickest way to do that is to use the identity we saw earlier. Indeed, it's a safe way to do it because we're given the 3 over 4. And when you develop that and do the numbers, you'll get minus 1 over 8. Now, if we stop to pause for a second, we agreed our angle x was something like this. And now we're asking what is the cosine of 2x. Well, if I double that angle, I will get into this quadrant because we agreed the angle is slightly more than 45. Now look closely at that. In this quadrant, the cosine will be a negative number and not a very big one. So that seems to make sense. Tan 2x, well, that's sine 2x divided by cosine 2x. So that's easy because we've figured out sine 2x already. It's 3 root 7 over 8. And we just have to divide it by cosine 2x, which is minus 1 over 8. And that gives us an answer of minus 3 root 7. Notice we don't have to start over again to find tan because we know sine and cosine already. Let's see another example. This one we're given cosine x is 4 over 5 and we're told the quadrant. It's in the 4th quadrant. Cosine x is 4 over 5. Now that puts us somewhere here. And we have to find sine x. Well, that's easy. We can do the square root of 1 minus cosine squared x, which is the square root of 1 minus 4 over 5 squared. And if you finish that calculation, you'll find we get 3 over 5. Or do we? Look carefully at the quadrant we're in. In this quadrant, sine is negative. Therefore, we take the negative root. And cosine 2x, the most efficient way is to use 2 cosine squared x minus 1, which is 2, 4 over 5 squared minus 1, and that gives you 7 over 25. So there's another example there of using the identity to find a trig ratio without actually finding the number. The angle, I meant. Okay, in our next video, we will use the double angle identities to solve equations. Hope you like the rainbow.